Hello, I'm Vincent Bichon, and this is Microvision, an augmented reality visualization tool for microservices. So microservices are an emerging trend in software development, enterprise software development. It's got its roots in service-oriented architecture, where functionality is split into individual services that are coordinated from an integration layer to create the overall functionality of the program. The difference is there's no integration layer with microservices. There's no central location for the business logic. Instead, it's all embedded inside the services themselves. Each microservice is responsible for handling its own communication needs. So this means the services aren't coupled at all except for the API they agreed to expose. The end result is highly scalable since you can scale up and down each of the services independently in a much shorter development cycle since each microservice is often developed by a separate team at their own pace. When it comes to deploying microservices, containerization technology is almost always used. This extreme decoupling comes with the cost of you're hiding important information inside the services. There is no centralized view of how all the services communicate and work together. Each microservice knows what it does, but no one has the overall picture. This means it's hard to visualize this system because it could be a very large, very interconnected mesh of services without a central view. It can be hard to identify where failures are happening at and how those failures propagate through the system. It can be hard to document all of this because each microservice is developed independently, with only agreement being on the API and no centralized models that everyone's working from. The result is that if you're trying to learn how an unfamiliar microservice system works, you're going to have to spend a lot of time trying to understand it. Because microservice architecture is still very young, analysis attempts are pretty new, but there are some established ideas. A lot of work has focused on extracting HTTP calls and then generating a communication diagram between the services. You can combine this diagram with other information to give you a central view of some aspect of the system. For example, one of the most complete examples is from Mayer and Weinreich, who combined the communication diagram with instance health and failure information to create this monitoring dashboard that you see here. Other examples include API versioning to create a dependency graph, or using known container vulnerabilities to create attack graphs. The problem is all of these use two-dimensional visualizations, which is fine for the three services that you see here on this dashboard, but this doesn't scale well. Microservice meshes can often reach dozens of microservices, and viewing those on a monitor would be difficult. A more suitable visualization tool for large complex graph systems is virtual and augmented reality. Instead of constraining yourself to a monitor that you have to scroll through, you can quickly physically navigate it and get a good at-a-glance overview of how the system works. This has been done quite a bit with large systems, for example, social networks by the RedGraph tool, and a bit closer example to microservices is a distributed system monitoring solution, and it showed a distributed set of servers as a single virtual server room. Now, this kind of visualization has not yet been applied to microservices specifically, but it has been used in software architecture in general. A well-known software architecture metaphor is the software city, where packages are large blocks that can be opened to examine their contents and show the connections between them, as you can see in this top picture here, and this has been ported over to virtual reality. A more specific augmented reality approach is software islands, which showed software modules as augmented reality islands, the packages in those modules as regions, the classes as buildings, and then imports and exports were shown as actual ports that connected to each other. My solution is Microvision, a combination of microservice, communication analysis, and augmented reality visualization. It shows the services as augmented reality nodes and the communication paths between them as edges. So just at a glance, you can see how many services you have, which communicate with each other, and the status of the currently deployed instances of your service. You can inspect the nodes and edges to get information. For example, if you tap a service, you can see the current instances that are running. If you tap one of those instances, you can get resource usage and error logs. If you tap a communication path, you can get all the endpoints that call each other between those two services. The other big feature of Microvision is recording and visualizing requests. When a request comes into the system, Microvision records it and it records all the HTTP hops that is generated between the services as a result. And it also records errors that get thrown during the handling of that request. You can then replay these requests to understand what exactly is happening between your services when it has to handle a request. All of this comes down to two basic goals. We want to be able to identify where exactly something went wrong in your mesh, and also be able to understand how the services work and communicate easily at a glance. For a user study, I wanted to focus on how quickly developers could use this system to learn a microservice program that they don't have prior knowledge of. This is a common scenario in real-world development. For example, if a new developer is coming onto a team, they have to get caught up to speed, or an entirely new team could be taking over an old legacy system. So for the participants, we had 20 software developers from a company that specialized in software as a service, and this company was already using microservice architecture. The developers were 20 to 40 years old, 14 were male, and they had all spent at least 6 months at this specific company. The population this represents is software developers who are familiar with microservices. And this population was chosen because we want to test how quickly you could learn a new microservice system, not how quickly you could learn microservice architecture. That would have to be a different study. We used the existing team structure the company used, so there are 5 members on each team for a total of 4 teams. And 2 of those teams were chosen for the control and 2 for the experimental groups. For this study, we used 6 Microsoft HoloLens head-mounted displays for the actual augmented reality display. The company provided the workstations the participants used, as well as the OpenShift cluster to run the sample application, and existing analysis tools to serve as a comparison. For the sample application, it was a practice exam administration tool for Texas teacher certification, consisting of 11 microservices, each of which had some basic UML documentation. We used the company's Jira platform for task administration. This was a 1x2 between groups study. The independent variable was the method of analysis, either the traditional tools or Microvision, and we measured how long it took to comprehend the system and how long it took to add new features to the system. For constants, we kept the same system between the groups, same documentation, the hardware available, the tasks to complete, and prior experience with microservices because they all worked for the same company. The study took place across 2 4-hour sessions, and the participants were given 2 sets of tasks to complete: analysis tasks, which measured how long it took them to comprehend the system. For that, they were just given a list of use cases and had to identify the services involved in serving those use cases, and then feature tasks to measure how long it took for them to develop new features. And this was just an exam statistics dashboard and a user feedback function. After a short tutorial, they were allowed to work as normal, with the exception that the control group could only use the traditional tools, and the experimental group was allowed to use Microvision. We monitored how long it took them to complete each task, as well as how often and for how long and for which tasks they used Microvision versus the traditional tools. After the experiment, we gave them a subjective questionnaire asking them how helpful their analysis tools were. So we saw that Microvision did help developers learn the new system, and we saw this in the shorter time to complete the tasks as well as positive feedback. But it was less used during feature development, and we think that's because the users reported it disrupted their workflow, which makes sense because you have to put on the head-mounted display. Also, it was less used alone and more in groups, and this could be because it's more suited for collaboration, or because it's less suited for individual use, or there could be a social stigma to using a head-mounted display by yourself. That would require a follow-up study. We think the main impact of Microvision is reduced maintenance cost. You're spending less developer hours on learning a new system, and so you can spend more hours on actually developing new features. Additionally, it can be used as an aid for documentation. You can make more understandable documentation since you understand the system better, and it could even be used to generate new documentation artifacts, 3D displays. Future work directions should focus on making it more helpful during the coding process, for example, adding more debugging capabilities like visually classifying different error types. You could also use the AR platform to display other system concerns, such as security or privacy policy violations. Thank you for your time.